So in this video we want to develop the formula for finding a tangent plane to a surface in space. So just to remind ourselves, the equation of a plane, which we developed in an earlier video, if we have a plane that contains a point, and we know a vector that's normal to the plane or perpendicular to the plane, we get the equation of the plane by multiplying the first component of the normal vector by x minus x sub 1. The second component of the normal vector gets multiplied by y minus y sub 1. The third component of the normal vector gets multiplied by z minus z sub 1, and this is set equal to 0. And what we want to remember is the main concept was that if we had a point in the plane, which is given by x sub 1, y sub 1, z sub 1, so this was our x sub 1, y sub 1, and our z sub 1, any other point is going to be an x, y, z in that plane. And we can construct the vector from x, y, z to x sub 1, y sub 1, z sub 1 by taking the change x minus x sub 1, this is a delta x, doing y minus y sub 1, or calculating a delta y, and doing z minus z sub 1, or calculating a delta z. So another way of thinking about a vector when we construct them by taking differences between points, we're really doing a delta x, a delta y, and a delta z. And then our perpendicular vector was the vector ABC. So it was perpendicular to, it has to be perpendicular to any vector in the plane. When we take the dot product, then we do ABC, and we dot it with our delta x, delta y, delta z. We took advantage of the fact that the dot product of perpendicular vectors had to be equal to 0. So the key is, if we want to find a tangent plane at a point, a tangent plane to a surface at a point, we need to have a vector that's perpendicular to the tangent plane. That's the first thing that we need to understand. So here I have a surface, and I have a tangent plane in lighter blue that's tangent to the surface at a given point. So this is my point x sub 1, y sub 1, and z sub 1. And what we need is to get the equation of this tangent plane, we need a vector ABC that is perpendicular to the plane, that hits this plane at a 90-degree angle. So what we want to do is get two vectors that lie in the tangent plane so that we can take their cross product. And what we're going to do is come up with a vector that is that lies in a plane that is parallel, to the x-axis, and then we want to come up with a vector that's parallel to a plane that lies in a plane that's parallel to the y-axis. And we're going to do this in a very specific way. So what we want to do is recognize if we have a surface, which I have here, this is a paraboloid, a downward opening paraboloid. If we have a surface z equals f of xy, when we calculate the partial derivative, partial z, partial x, which is equal to, another way of saying this is f sub x, right? So when we do this calculation and find f sub x, we could always write it over 1 and it would still be f sub x. And what we want to recognize is that partial z is just another way of saying dz over dx. This is how we write dz when we're taking a derivative of two variables. This is how we write dx when we're taking a partial derivative, when we have a function of two variables. And dz, we want to recognize that dz and dx are just ways of saying delta z and delta x, right? dz is just a change in z, and dx is just a change in x. Partial z is just a change in z, and partial x is just a change in x. It's the name that we give them when we let the change in z and the change in x become infinitely small. So what we want to recognize then is that we can construct a vector from this, just like we saw in the previous slide, where we recognize that taking the difference between x coordinates, the difference between y coordinates, the difference between z coordinates gives us a vector, but it's really just delta x, delta y, delta z. We want to take advantage of the fact that the partial derivative is just a change, right? And in fact, f sub x, because it's in the numerator position, I wrote it over 1, is the change in the z direction, and 1 is the change in the x direction. So I can construct a vector from this. I can say dx, or delta x, partial x, or delta x is 1. The change in x is 1. The change in z, dz, is just f sub x. And because we took a partial derivative with respect to x, we held y constant to take that partial derivative. So the rate of change, or the change in y, is going to be 0 because we hold y constant. And so this gives us a vector that is tangent to the surface, right? Because the derivative, f sub x, this dz dx, is the slope. When we calculate it at a specific point, it gives us the slope of the line at the point. So by constructing this vector 1, 0, f sub x, we've constructed a vector that is tangent to the surface at a point the moment that we evaluate it, right? So if we take f sub x and we evaluate it at x, if I label this x1, y1, z1, I'm going to evaluate the derivative at x1, y1. If I called this point I'm interested in x naught, y naught, z naught, then I would just evaluate my derivative at x naught, y naught. And the moment I do that and plug that value in for f sub x here, I have a vector that lies in a plane that's parallel to the x-axis and that is tangent to the surface at that point. And if it's tangent to the surface, then it has to lie in the tangent plane at that point. And then we can play the same game by taking the partial derivative, partial z with respect to y. Partial z, partial y is just, this is the change, right? When we calculate this is change in z, or delta z, over change in y, or delta y. So we can, if I write it over 1, just like I did here, I can construct a vector that gives me this, that tells me how things are moving in a plane parallel to the y-axis at this point. And that vector is going to be tangent to the plane, and I'll have two vectors that are tangent to the plane, and if I take the cross product, I'll get a normal vector to the plane, or perpendicular vector to that plane. So my vector is going to be, hey, if I take the derivative with respect to y, I'm holding x constant, so the change in x will be 0. The change, if we hold of a constant, is 0. And then my delta y is in the denominator, there's a 1, and my change in z, delta z, is f sub y. And I would just need to evaluate it at the point I was interested in. And so the idea now is I have two vectors that lie in the tangent plane, and I just need to take their cross product. So we know how to take a cross product. We go I, j, k, and then we dump the two vectors in. So for example, we dump in 0, 1, f sub y, dump the other vector in 1, 0, f sub x, and then take their cross product. So we get I times, we strike the row and the column out, we get 1 times f of f sub x minus 0 times f sub y. It's just an f sub x. Plus, so actually it's minus, we get minus, and then we do j times, we cross the column and the row, we do 0 times f sub x minus f sub y times 1 is minus f sub y. And then we get plus k, we strike row 1, column 3, we get 0 times 0 minus 1 times 1 is negative 1. So we wind up with the vector, if we write this in vector form, a component form, we get f sub x, the opposite of a negative is going to be f sub y, comma, and we get a negative 1. And this is the vector then, that as long as we evaluate this vector at x naught, y naught, this vector is perpendicular to the tangent plane. And the moment I have a vector that's perpendicular to the tangent plane, life's good, because I take that vector, f sub x, f sub y, negative 1, and I dot it with the set of all vectors that lie in that tangent plane. And that's going to be given by x minus, if this point right here is the point x naught, y naught, z naught, then I'm going to do x minus x naught, y minus y naught, and z minus z naught. I get that vector delta x, delta y, delta z that lie in the tangent plane. And because those two vectors are perpendicular, this is perpendicular to the plane, this lies in the plane, so their dot product has to be 0. And we know how to calculate a dot product. So the next slide kind of summarizes it. You take that vector f sub x, f sub y, and -1, and you dot it with the delta x, the delta y, and the delta y and the delta z, and that dot product is going to equal 0. And we just need to make sure we evaluate our f sub x and our f sub y at the point we're interested in. So if I do a little bit of shorthand notation, I could just say f sub x. We could just say f sub y right here. I should have put my cheater readers on because everything's looking blurry to me. Forgot to put them on before I started. So we could shorthand notation it by just doing the f sub x, the f sub y, but we would need to recognize that if we want the tangent plane at a point x naught, y naught, z naught, we have to evaluate our derivatives at x naught, y naught. That's the first thing we need to recognize. And then we can change the form of this a little bit. So right here, my delta z term, z minus z naught, if I distribute the minus in, or the subtraction in, I get minus z. I can then add z to both sides to get a z by itself right here. And then I get minus, minus, so a double negation would give me a plus z naught. So here's a plus. And then we want to recognize that if z equals f of x, y, then to find z naught, you would just evaluate the function at x naught, y naught. So the plus z naught can be replaced with plus f of x naught, y naught. So that's the general development of the equation of a tangent plane. And the key idea is, the other key idea is, when we were working with functions of a single variable, we were interested in tangent lines, and that's because that's what we could talk about when we were in two-dimensional space. I have a curve and I have a point on the curve. Well, I can get the line that's tangent to the curve. But now we're in three-dimensional space, so at the point there's going to be infinitely many tangent lines at a point, but those tangent lines, when put together, form a tangent plane. And so we're interested in finding the equation of that tangent plane rather than a tangent line.